Hello, welcome back. So, in the previous lecture we discussed about Stokes flow past various particles, for example cylinder and then a sphere we have discussed, and now we move on to something called lubrication approximation. So, most of the biological applications and also fluid machinery, so they very much involve this lubrication approximation. So, as the word says lubrication, you can recall. So, many times we use when there are some thin plates come in contact. So, then we will patch up with some lubricant. Okay. So, that is to avoid the wear, right, okay, friction, so that the machinery is not damaged. So, understanding the lubrication approximation and the corresponding physics and the dynamics is very much essential to understand such machinery. Okay. And also at micro level at various biological phenomena, such lubrication assumption is very much valid. Okay. So, let us look at the lubrication approximation. So, we generally start with the corresponding governing equations, which are Navier-Stokes, but as we have seen, suppose you have a unidirectional flow, then the complete Navier-Stokes equation got simplified to very simple linear equation, and then we could get the solution. Similarly, instead of handling full Navier-Stokes equations, maybe under some approximations the system will be reduced, and then that will reflect the corresponding physics of the problem. So, same thing may happen here. Okay. So, what is the lubrication approximation, and then for regular as well as irregular geometries how things can work. So, we will see in brief. Okay. So, let us see. So, lubrication theory describes the flow of fluids in a geometry when one of the dimensions is significantly smaller than the other. Okay. So, this is we are talking about regular or irregular geometry. So, when we say one of the geometry is smaller than the other, so naturally one can bring the concept of aspect ratio. Okay. So, when a large aspect ratio, then how the corresponding approximation controls. Okay. So, in case of a regular geometry, we are talking about regular in the sense you have say two parallel plates which are separated by a distance h, and then let us say length of the plate is L. Then if we introduce the aspect ratio, which is h by L. So, when h is much smaller than L, that means compared to the length of the plate, if the distance between these two is small, so then one can have the corresponding aspect ratio which is much smaller. Okay. So, this is the aspect ratio. When this is much smaller, what happens to the corresponding Navier-Stokes equations. So, that is our idea to understand. Okay. So, in case of irregular, we have wavy channel, okay, and then see the mean width is this, and then the corresponding wavelength is L. Okay. So, then you can introduce the corresponding aspect ratio again in this case h by L. Okay. So, now it matters. So, how it matters? So, you have, so this is h and this is L. So, if h by L is small, so we boil down to something like very narrow scenario. So, this is a lubrication or sometimes capillary type. Okay. Similarly, so if we have such scenario, so when we have corresponding h by L is small, okay, that is h by L, you can define some aspect ratio, this is much. So, then what happens? We are talking about very thin. Okay. So, most of the capillaries, for example, biological tissues, arteries, etc. So, they have such configurations. So, it is very much essential to understand the physics under this approximation. So, when we say h by L is much smaller, so naturally what we are trying to do is probably we are trying to neglect the higher order terms. Okay. So, we consider the corresponding governing equations. So, to start with we consider equation of continuity, and then we would like to fix the length scales, various length scales. So, this is a full Navier-Stokes equations we have considered. This is the x momentum and y momentum in component form. So, we have discussed already how to write from the vector equation. Okay. Now, we would like to fix the corresponding non-dimensional length scales. Okay. So, for t we are introducing characteristic time, and for x since we are considering, let us say, rectangular geometry, parallel plates which are separated by distance h. So, along the direction of the flow we have L, and perpendicular we are using the corresponding distance between the plates, and for u velocity assume you have a unidirectional flow kind of, or in general flow along x direction. So, we are using a characteristic velocity, and for pressure we are not fixing the corresponding non-dimensional group a priori. The idea is we will non-dimensionalize and then use the lubrication approximation, and then we will see how the pressure can be estimated in terms of various dimensional quantities. So, hence we just declare a non-dimensional characteristic pressure and assume that that is normalizing P, so that we get a non-dimensional pressure. Okay. So, now let us consider the equation of continuity. So, we have various length scales which we have fixed already. So, we are considering equation of continuity. Okay. And we have the length scale, and for u we have used. Now, our aim is to estimate the corresponding non-dimensional group for V. Okay. So, if we do that, and here for x we have x by L, and for y we have y by h. Okay. So, if we do that, okay. So, here we get h. So, let us call some V star which we are trying to estimate. Okay. So, this is a non-dimensional u, non-dimensional x, non-dimensional y, right. So, then plus we get L by u h okay. So, this indicates the non-dimensional grouping for V star should be okay. So, this is the non-dimensional grouping for velocity to be non-dimensionalized. So, here so the lubrication approximation, before we ensure the lubrication approximation, what we have seen. So, along the flow direction you have a different scaling, and vertical you have a different scaling, okay, and we would like to see the corresponding contribution. So, we have the normalized continuity equation. Okay. So, now we try to non-dimensionalize the x momentum equation. Okay. So, I will show for x, then y we can do it. So, we have the Navier-Stokes equation. Okay. And just now we have obtained for V, V is okay. So, this is the scaling. Of course, we have T, so we can introduce. So, correspondingly if we do, so there is a U, so it is very straightforward, we get this. Then here one U and another U, and we have a length here. Okay. So, this is very straightforward, we get U square by L, but here we have to check because V has a different scaling. Okay. So, V is producing UH by L, this is for V, and then we have dou U by dou Y. So, that will produce U by H. So, this is again we are getting U square by L. So, therefore, we get so this is the scenario, and for P we have corresponding normalizing is done by P, and then we have L. Okay. So, we are because rho I have brought it to the other side. Okay. So, what we get is we get minus P by rho L. Now, here we get different scalings because of x scaling and y scaling which are different. So, we get different scaling. So, mu by rho is nu. Okay. If you consider, we get u and here we get h square. Okay. Here u and y square. So, y square is corresponding to that, what we get is, so we have for u we get this, then corresponding to y square we have to divide by h square. So, you get h square. Okay. So, this is the term which we get the scaling for this term, and similarly for this if you do, and here L square. So, u by L square. Okay. But we would like to take u by h square common. So, this comes straight away. So, therefore, we get here u prime by y square, but for x if you see we have u by L square coming out, but we would like to take h square common. So, therefore, so we get this. Okay. So, the aspect ratio exclusively as a non-dimensional parameter is appearing in this. That means, if at all one would like to go for a lubrication approximation, that is you call it the aspect ratio h by L, and if you go for this assumption, then what we are trying to do is definitely we would neglect is much smaller than 1. Okay. So, therefore, we are almost trying to neglect. So, in which case the corresponding lubrication approximation is going to reflect and it is going to suppress the corresponding axial variations. Okay. So, any case, so this is non-dimensionalization we have done, and a similar non-dimensionalization. So, that is what is given exactly here, and so this is a simplified version. Okay. So, once we have this, the prefactor that we have mu u by h square. So, we have divided by that. So, once we divide we get this. Okay. So, if you pay attention, this is nothing but Reynolds number. We have done the non-dimensionalization. So, this is nothing but the corresponding Reynolds number, and h by L is the aspect ratio. Then here h square by nu is the diffusion time. So, exactly you are getting the non-dimensionalization of T, T has to be of order h square by nu. Okay. So, that is so for shallow layer, that is the lubrication approximation, h by L is much smaller than 1. So, therefore, we assume this is a smaller. Now, our aim is to study the approximation under small aspect ratio. Now, if you go for small aspect ratio, you see for this term you have a Reynolds number. Now, if Reynolds number is growing, even if you control h by L much smaller, so the total contribution of the term will be depending on Reynolds number and the corresponding growth of Reynolds number. So, our aim is strictly to consider the lubrication approximation. So, in order to control that, we are assuming the Reynolds number is of order 1, so that we capture the h by L much less than 1. Okay. And we would like to have the steady behavior. So, we are assuming the corresponding diffusion time scales are very small. So, we are neglecting that. Okay. So, once we have such a small parameter identified, so we are approximating this with an assumption that consider only terms of order h by L and then h by L square onwards, h by L and square everything is neglected. So, that means we are considering constant terms, and then since this is much smaller, we are omitting h by L and then higher order terms. So, this is gone because of the steady assumption. Then since h by L is small and this is restricted to order 1, so this term is gone, and we have the corresponding right hand side. We have got the if you see one can get the corresponding non-dimensional group for P. Okay. So, the remaining whatever is left out, that is exactly the non-dimensional grouping for P. Okay. And since h by L is small, this is also gone. So, we get the corresponding x momentum equation under lubrication approximation. Okay. So, in dimensional form we get this. Now, this is the x momentum, and similar analysis we do it for y momentum. So, I have shown it for x, you can do it for the y momentum, and then under lubrication approximation you would see the corresponding pressure gradient vanishes. So, that is the equivalent. So, we have the corresponding x momentum and y momentum under lubrication assumption. Okay. So, what is happening here is the in the inertia which we have neglected, okay, that is reflected by slow flow through these gaps. Okay. So, that is reflected in this sense. Okay. Now, we would like to get how the solution behavior of such lubrication approximation can be estimated. Okay. So, before we do that, so there are a lot of applications, okay, as I mentioned. So, one application is flow between thin plates with some objects included. So, this is popularly known as a Healy-Shaw flow. So, here it is like very thin plates are coming in close contact and there is an object placed. So, this can be solid object and sometimes viscous drops. So, there are several applications of this problem and very popular, and in order to solve the flow, since the gap width is small, so you can expect the vertical variations are not normal, okay, like you need not consider full variations. So, what is the corresponding vertical variations happening, that is reflected in the y momentum equation, which is simply the corresponding pressure gradient is 0. Okay. So, that is the power of lubrication approximation. Okay. So, this is again coming to the Healy-Shaw flow. So, we have a plate, two plates located at a distance h, and then there is some kind of object. So, viscous fluid flow with this velocity in a narrow gap, and then the plates are located at z equal to 0 and h, and the flow is assumed to be driven by pressure gradient. Then if we go for the corresponding lubrication approximation, in the earlier case here we considered only x and y momentum equations, okay, 2 dimensions. But here in this application what we are showing, we have UVW. Okay. So, correspondingly if you go for lubrication approximation, what happens? See, the aspect ratio is the competition with the h along x and h along y. So, these two aspect ratios they will come into play, right. So, and we are assuming that h by the corresponding length scale, which we use it for x and y the same length scale. So, that is small. So, therefore, similar to the 2D case that we have done, if you follow the lubrication approximation, what we get is the corresponding x and y momentum, you get contribution of the velocity, whereas for z you will get the corresponding pressure gradient is 0. Okay. So, that is what we get. So, if you go for the lubrication approximation, you see that x momentum you have a pressure gradient which is balanced by the corresponding variations of velocity along z direction. Then similarly, y momentum variations of v along z directions are balanced by the corresponding pressure gradient, and in case of z momentum you have the corresponding pressure gradient vanishes. Okay. So, now we would like to attempt solution exploiting the fact that dP dz is 0. Okay. So, since we have z derivatives here, so and the fact is dP dz is 0, we can integrate this 2 times with respect to z, because this is independent of z. So, we can integrate each of these equations 2 times with respect to z and get the following solution. Okay. So, this involves each of the velocity components involves 2 arbitrary coefficients. We could do this because of the corresponding lubrication approximation. Okay. So, once we have this, we can eliminate these arbitrary coefficients using the boundary conditions, which are typically we are using no slip at both the plates at y equal to 0 and y equal to h. We are using no slip, and that will determine the coefficients. One of the coefficient here will be 0 and one of the coefficient here will be 0, and the other non-zero coefficients a and c are determined in terms of the corresponding pressure gradients. Okay. So, we have the complete velocity structure. Okay. So, now if you closely observe the velocity structure, what we have, u behaves like so we have z h minus z and v okay. So, this is function of z and this quantity is independent of dou p dou z is 0. So, p is independent of z. Okay. So, what we can do, so this is common. So, we can introduce, say, define some phi which is p z. Okay. Then we can realize x is exactly and this is exactly. Okay. So, once we have this structure, what we are trying to do is we are trying to define a function phi such that d phi by dx okay, and we can even absorb this in this. So, we can define minus where we have absorbed okay. So, this relation, which means we got the corresponding vector, of course, in 2D. This is gradient of, this is again 2D. So, we got a velocity potential. Okay. So, what we got is the corresponding lubrication approximation. If you do, so then the corresponding two dimensional velocity components can be expressed in terms of a velocity potential. Okay. So, that means even though you have highly viscous flow, what we got is there are no rotations and it is captured by only the potential flow. Okay. So, that is a very interesting observation. So, now once we have the corresponding phi, the advantage is we can get the solution in terms of phi, right. So, how do we get the solution in terms of phi? So, this I have explained. So, we got the corresponding velocity potential, which is given by this, right. So, now our aim is to get the solution, we have to get the equation satisfied by phi. Okay. So, that is nothing but once we have the divergence free, then we get phi is harmonic, okay, which means under lubrication approximation it is enough to solve a harmonic function, okay, instead of solving the complete component equations. That is a great achievement. Okay. So, now the equation satisfied by phi can be obtained directly by taking divergence, or other words we can also integrate the corresponding mass conservation across this. Okay. So, that is what we have done. So, then we conclude that P is harmonic or the corresponding potential is harmonic. Okay. So, this gives additional flexibility in case of lubrication approximation. You need not solve the complete the component equations. It is enough to solve one velocity potential, which is a scalar equation. Once you get the solution, we get the corresponding velocity, and then we can integrate for getting the pressure. So, there are several applications as I indicated, and typically when it comes to lubrication approximation, the first and foremost example comes to anybody's mind is the bearings. So, the bearing structure involves two metals which are in close contact, but they have to produce a nice frictionless rotating system, right. So, these are typically used in various rotating equipments, okay, in motor vehicles and bicycles, etc. So, there the corresponding lubrication approximation will be used. Okay. So, you can see, so this compared to the length scales, the width is very small. So, one has to go for corresponding lubrication approximation. Okay. And another several applications are there, but we would like to show one of our contributions using lubrication approximation. The problem is as follows. So, when large objects are sunken in sea, so how do we lift it? Okay. So, this is the bottom of the sea, and this is the interface where you have a flow, that is a liquid above, and then this is the porous bed. Okay. So, please ignore about this, what is anisotropic, etc., we need not. So, porous bed, that is a sea bed which consists of sand, and then on top of it we have a water. Okay. Then when object is sunken, what happens? If you visualize, the object will be slightly floating, okay, due to the corresponding buoyancy effects, right. So, once it is floating, our aim is to lift it, right. So, how do we do it, this mechanism? Simply we do not go and then execute with some crane. Okay. So, you have to estimate what kind of object, and then what will be the forces with which you lift, so that the object is not damaged, etcetera, right. So, now in this, if you visualize, there will be a thin gap where the object is floating, and then if you start lifting, so initially flow is coming from the bottom, and then once you try to lift, so within this gap you have a lubrication approximation. So, once you start lifting, so then the flow comes from the side, and then you have to overcome the corresponding lubrication force. Okay. So, with this idea, this particular problem has been solved, that has appeared in this article. Since we are talking about lubrication approximation, to make you realize that there are various real life applications, we have given this. Okay. So, you can see here H is gap between the bottom of the object, of course, here we are assuming flat, and then again flat bed, and the corresponding L is the length of the object. So, H by L is small. So, we are in exactly similar scenario as what just now we have seen. Okay. So, with this I am sure you get an idea of how the lubrication approximation works, and that will ensure that you can simply solve a scalar equation. Okay. So, we see this applications of lubrication approximation in coming lectures. Thank you.